All right, so we're gonna look at some homework problems, 4.6, limits at infinity and asymptotes. And we've got this one right here. So let's see, we have a degree 1 binomial times a degree 1 binomial. So there's a quadratic in the numerator, quadratic in the denominator. And so the trick I'm gonna employ for that one is like trick I used yesterday. Let's see what happened. Did we lose Cole there? Bummer, Cole's having internet troubles again. All right, so the trick on regular rational functions like this is to determine what is the highest power of x. Well, ultimately, if I multiply this out, it would be x times x or x squared, and then we divide by that highest power. So what I want to do is I want to divide the numerator by x squared, and I want to divide the denominator by x squared. And to do that, since these are two binomials of first degree, I'm going to split the x squared into x times x, and I'm going to divide x into each binomial. So this becomes the limit as x goes to infinity. Alternatively, we could multiply it out, but I don't feel like doing that today. And again, I'm going to look at x squared as x times x, and then I'm going to divide this by one of those x's. So that's going to give me 7 over x minus x over x, which is 1. And then I'm going to take the other x from the x squared and divide it into this one, which is going to give me 6 over x. And then 6x over x is just 6. In the denominator, similar thing's going to happen. We're going to split that x squared into x times x, and we're going to divide that x into each of those. So 3 over x minus 7x over x is just 7. And then 10 over x is 10 over x, and 8x over x is just 8. Now, if the limits exist, I can take the limit of each component in the numerator and each component in the denominator. So let's see what happens. And I'm relying on a fact that we should be familiar with, that the limit as x increases forever of 1 over x is 0. So this is a fact that we need to use here, because then this chunk right here goes to 0. This stays at -1. This chunk right here goes to 0. That stays at 6. There's no x. This chunk goes to 0, and this chunk goes to 0. So I get -1 times 6 over -7 times 8. And this cleans up just a wee bit. I can divide a 2 into the top and bottom. And so I get -3 over -28. So I guess the whole thing's positive. So let's just ditch the negative. 7 times 4 is 28. Yeah, so this I should find is going to 3/28. And we could look at the graph and see that that's the case too by just looking out way to the right to see if it doesn't look like it's going to 3/28. So let's get a graphing computer out. I'm going to use Desmos. No, I lied. GeoGebra, because I like the way it scales axes. And then I just need to type this correctly. So I'm going to bring this over here so I can see it. All right, so I'm going to treat this as a function. F of x equals fraction parentheses 7 minus x times 6 plus x squared. And so it is important we use our technology wisely, and I think this is a wise use of technology to see if that wild math I just did really is legitimate. I wish they had these when I was in college. So much more fun. That's not true. I had a heck of a lot of fun in college doing calculus, even without a graphing calculator or a computer like this. All right, so then what I want to look at is if I look way out to the right here, what's going on? So I'm going to do two things there. I'm going to graph that y equals 3/28 and see if it looks like that's what this is approaching. So to do that, I'm going to rescale by expanding the y-axis in that way, or zooming in on the y-axis, I guess I'm doing there, and then zooming out on the x-axis to see if that looks like a horizontal asymptote. And it is a horizontal asymptote, right? That looks pretty good. So I think the work we did looks good, right? And I could zoom in further just to see what's happening there. Remember, it is possible for a function to cross a horizontal or slant asymptote before it starts to suck up to it, but it isn't possible for a vertical asymptote because that involves division by 0, which is kind of an explosive event. All right, that was fun. Next. So the next one had a whole bunch of them, and I'm not going to do all of them. I'm just going to do a couple because the approach I showed there works on each of them, except the square root ones. Where'd it go? Oh, it's on the screen. Come back here, please. There we go. All right, so number 8. I was listening to my recording the other day, and I say all right a lot. I'm going to try to come up with a new word instead of all right. So the first few limits here are related to limits that you learned about in pre-calculus. If the degree of the numerator and denominator of the top are the same, then those terms take command over what's going on. We could use that divide trick here to see that. And so based on the work I did earlier, I would claim that this limit here is just -8/2, which I would reduce to -4. So that would be the answer there. Let's try a different one. Here, the degree of the bottom is bigger, and so there's a few ways to approach that one right there. But since the bottom overwhelms the top gets bigger way faster than the bottom. This one right here is going to go to 0. The bottom one, the middle one here is kind of fun because the degree of the top and bottom, oh, I thought the degree of the bottom might have been bigger. No. All right, so that's a lot like number 1. We're going to skip that. Let's do the 4th one here, or the 5th one. And negative infinity, that looks like more fun. Okay, we're going to do the hard one. The others aren't too bad. We only need that part. And off we go. Okay, so what to do with that one there? So x is approaching negative infinity, so that's like approaching infinity, but we get negative results. So we have to consider the sign of what's going on here. And looking at this right here, we've got the square root of x squared going on there. So again, here, think about this. This means really big numbers. So for really big numbers, the square overwhelms the linear term. So my guess here would be that this is a lot like the square root of x squared. And in the bottom, the 4 is, negligible. Who cares about 4 if you have a trillion? So the -13x takes over on the bottom. The square root of x squared is really the absolute value of x. So I have -13x in the bottom, and I have negative numbers here. So that means the denominator is negative. The numerator, at least the x is negative. The numerator is positive. Negative times a negative is positive. So I have a positive number over a positive number. And it's really x over x, which is like 1. And then I have a 13 in the denominator. Oops. And again, I have a negative times a negative in the bottom. So it looks like this is going to go to 1/13. So another way to look at this right here is that trick I showed earlier with a slight modification. So the highest power really is x here, because the square root of x squared is absolute value of x. So what I'm going to do is I am going to multiply top and bottom by 1 over the square root of x squared, based on this idea right here. So I'm going to call that 1 over x right there. And then this is going to be 1 over the square root of x squared, which is kind of like x. And again, I got to keep into account my sign analysis up there. That might come in handy. The useful thing in the numerator here now is I have a square root divided by a square root there, and ignoring the signs for just a moment, I can bring those together. So that's going to be x, oops, sorry, my pen's doing its freaky thing again. That's x squared plus 11x over x squared when I bring these two together. And in the denominator, like before, that would be 4 over x minus 13x over x. Let's write that out. And then this simplifies a bit. X squared over x squared is 1 plus 11 over x inside the square root. And in the denominator, I have 4 over x minus 13. And again, think about the sign analysis here. X really is a negative number there. Let's see. And I kind of dealt with that up there, that the result's going to be positive. So then here, once I take the limit in, this is going to go to 0. And I'm ignoring the sign of infinity for a moment because I thought about that already. That's going to go to 0. And so then I get the square root of 1 over negative 13, which is 1 over negative 13. But x is really negative numbers, so I really get the opposite of that in the end. So this should be 1/13. That one was a little harder because we had to pay attention to the signs of what was going on. And then there were a couple of ways to think about it that way or this way. So you can try that one. Before that was a little bit easier. All right, next, number 11. So we're approaching pi over 2 from the right side, and then we're approaching 3 pi over 2 from the right side. And this indicates a vertical asymptote. Okay. So if we look at the graph here, this is the graph of the tangent, and and let's see, yeah, pi over 2. Pi over 2 on the right side, so that means we're on this part of the curve over here. So let's actually get a graph of that in Desmos or GeoGebra, just for fun. Tangent of x equals the tangent of x. Zoom in. I really only care up to 2 pi. Maybe there. And then I'm curious about x equals pi over 2. And I'm on the right side of that, so I have points over here. So let's throw a point on there. And show the value of the point. So as we approach pi over 2 on the, stop it. As we approach pi over 2 on that right side here, we can see that y value is dropping down over there. And just another way to think about this for fun, we've got the limit as x approaches pi over 2 on the right side of the tangent of x. Now, tangent is really sine over cosine. So let's look at this as the limit as x approaches pi over 2 on the right side, sine of x over the cosine of x. And I'm going to think about that for a minute just on the unit circle. And on the unit circle, I really only need to see the top part here. And an angle of pi over 2 puts us over here at this point. And remember, on the unit circle, x value is the cosine of the angle, y value is the sine of the angle. And at that point right there, x is equal to 0 and y is equal to 1. So in the sine over the cosine, as x approaches pi over 2 on the right side, so that's from this side over here, let's get another color. So I'm approaching that point from this side over here on the unit circle. The sine is getting closer and closer to 1, and the cosine is getting closer and closer to 0. It's 0 from, let's see, on the right side. Oh, I'm on the wrong side. I lied. The right side on the x-axis, not on the unit circle, means I'm looking at numbers x is greater than pi over 2. So that means I'm really on this side over here. Sorry about that. And on this side over here, cosine is less than 0. It's a negative number. So I'm at 0 on the left side there. So I have 1 over an increasingly small negative number, which is going to give me a large negative number. And so in the limit, it's going to be a negative infinity. And we can see that on the graph too. And then the other one was 3 pi over 2 on the right side. So here's 3 pi over 2. Let's look at it in the graph and think about the unit circle. Graph. Let's go. X equals 3 pi over 2. And oh, that's interesting. It usually converts my pi when I, oh, there it goes. When I hit enter, there we go. So here's 3 pi over 2. And I am again on the right side. So I have a point over here. Make sure I got that right. Yeah, we're again on the right side there. Space. There we go. And nice thing about GeoGebra is I can ask it to show me the value. So similar to before, as I move that point, I'm having a hard time tracking there. I can see as the x value gets closer, the y value is dropping there. So same idea. As x approaches pi, 3 pi over 2, excuse me, from the bigger side, so that means x is a number that's greater than 3 pi over 2 of the tangent of x. Again, we get that negative infinity. And that's the definition of a vertical asymptote. The x approaches a fixed number and the y approaches infinity or negative infinity. So we have a vertical asymptote. Of x equals pi over 2 in the first case, x equals 3 pi over 2 in the second case. And in general, right, we can make a generalization on that by realizing how far these two apart are, and they are pi apart. If you subtract pi over 2 from 3 pi over 2, you find they're pi apart, and that happens every pi, which is kind of cool. So if we wanted to generalize this further, we could take that pattern and say, if we take x and then starting at pi over 2, we add on multiples of pi, where n is some integer. Then we've named all of the vertical asymptotes with that expression there. If we wanted to think about that in the unit circle, we still could do that. So if we continue the unit circle down here, this is 1 pi over 2 up there, 2 pi over 2 is there, 3 pi over 2 is down here, and then over here we get to 2 pi. So we're approaching with values that are angle values that are greater than 3 pi over 2, which puts us here. So we're coming across from that side there, and that point right there is x equals 0, y equals -1. the x values are on this side over here. So x is positive as we approach. So if we think about this as the limit as x approaches, oops, sorry about that, 3 pi over 2 from the side that's greater than 3 pi over 2, sine of x over cosine of x, then what we have is that the sine of x is approaching -1, and the cosine of x is approaching 0, but from the positive side. So I'm getting a smaller and smaller denominator, a numerator that's heading to -1, so this should head to -infinity with that analysis there. So a couple different ways to think about that, unit circle wise or just looking at the graph. Next. So I think number 12 was mentioned next. Okay. Screenshot that sucker. Oops, button. All right, so let's just think about this function right there. So y equals the opposite of the sine of 4x minus 2, and then we have a -4 outside of that. So there's a bunch of transformations down here. This one right here changes the period, or the frequency of the graph. That isn't the period, it just affects the period, right? We divide by that. So this just oscillates more often. The period here would be 2 pi over 4, or pi over 2. This right here, if we pull the 4 out, would be a shift. Let's see, what's the right word for that? A phase shift is what we call that one. And the phase shift, you have to factor that. So 4x minus 2, I'd factor out the 4, which would leave me with x minus 1/2 if I factor out the 4. So the -1/2 is actually the phase shift. This right here gives me the new center line, the new average of it. So this is centered on y equals -4. And this right here is just a vertical flip, right? Now, thinking about the sine in general, some things we know about the sine of x, forget about all those transformations, is that it oscillates between -1 and 1. And the negative just flips that, which really doesn't change anything. This is just horizontal movement. That doesn't change this right here because the sine here I'm thinking about as a y value. This stuff doesn't affect the y values, only the x's. But this does matter. So if I subtract 4 from each side, then I get the sine of x minus 4 is going to oscillate between -3 and -5. No matter what x is, so this phase shift and period shift doesn't matter too much. It's just shifted over a little bit and it just oscillates more frequently. No big deal. But bottom line here, this is for all x. So it doesn't matter how big x gets here. This is true for x big or small. So that limit there is trapped between -5 and -3. So if I take the limit of each piece here, and we can put that stuff back in, we're going to get the limit as x goes to infinity of the negative sine of 4x minus 2 minus 4 is trapped between -3 and -5. And it just depends on which big x value we pick. We could be at -5, we could be at -3, we could be somewhere in between. So the limit does not exist because of that oscillation. All right, let's get one more problem that wasn't in the homework. I thought I put it in there, but I must have forgotten. Let's consider the sine of x over x. So you may remember this limit from way back in the beginning of the course, where we considered the limit as x approached 0. And what we discovered with a bit of geometry that we had to apply related to the unit circle, that limit right there was 1. So next we're going to take a look at, well, what if instead of approaching 0, we see what happens as x goes to infinity? So now I want to look at this one. I don't think we looked at this way back when. Sine of x over x. I want to know what's going on here. Is it like the previous problem where the limit doesn't exist because it gets to bounce around between these two numbers forever, or does something else happen? So I'm going to go back to that idea I had a minute ago, which was that in general, the sine function oscillates between 1 and -1. And then I'm going to tweak it by dividing by x all over here. Now, I'm not too worried about dividing by x. X isn't going to be 0 here because x is getting to be big, and big is away from 0. So I'm dividing by big numbers. Now, if I then take the limit through here, the limit as x goes to infinity of this first piece, we have applying the squeeze theorem here, which I was trying to do in the previous case, but it didn't really help, just showed me the limit didn't exist. I get this inequality. And what do we know about this inequality here? Well, this right side here, as x gets big, the whole fraction goes to 0. Now here, I just have negative numbers over a big positive number, which still goes to 0. So this limit there is trapped between 0 and 0, so it must go to 0 too. We're squeezing it in there. And we can see that if we look at the graph. So my claim based on the squeeze theorem here is that this limit is 0. And this is a cute one to look at. Let's get a new page. Or we can just reset here. Page is easier. So I'm going to look at 3 different functions here. My original function, f of x, the sine, of x over x. That mistype reminded me of a funny joke. I'll show you in a second. And then I'm just going to look at y equals 1 over x and y equals -1 over x. Just come here, please. There you go. And I want to see what's happening to the sine here. So I'm just going to use GeoGebra's rescale tool here, which is the move graphics tool, where I can grab the axis and do this. And then we can zoom in a bit there. Oh, that's beautiful, isn't it? Math is awesome. Yeah, so we can see here that this sine of x over x is trapped between 1 over x at the top and -1 over x below. And as we look out, it's just going to keep bouncing between those two. Those two functions have a horizontal asymptote of x equals 0, or sorry, y equals 0, the x-axis. And so this wave is just going to keep getting shorter and shorter and shorter in amplitude, trapped between those other two functions forever and ever and ever, and it eventually just gets squashed in the end. But there is no end, right? This is infinity. But in the limit, it gets squashed to 0. Pretty cool, huh? All right, we did a whole bunch of limits there. Cool, fun stuff. We're ready to move on.